Hello and welcome to section 3.7 optimization problems. In this section we are going to do a lot of word problems dealing with the maximum, minimums, and things like that that we've been finding throughout this unit. Just as a word of advice, if you have any questions about these, please come to class prepared to ask them. Also, please look around for other videos on this stuff to make sure that you really understand it. There are thousands of them out there. You just need to look and see if you can find anything that will help you along your way. Alright, so basically what we're trying to do in this one is it says for which points on the graph are of the graph 4 minus x squared are closest to the point 0, 2. So basically we're looking at a parabola. As you may know, you're looking at a parabola that is upside down and up 4 units. So I'm just going to quickly sketch a parabola that looks something like that. And so we're up 4 units. You'd have a parabola that looks like this. And we're looking at the point 0, 2, which would be about halfway up. And so we're trying to find a point somewhere out here that is closest to that point. Alright, and so that's what we're trying to find. And so basically, what are we trying to find? Well, we're trying to find a length of a line. And when we try to find the length of a line, we have to remember distance formula. And so when you're doing these problems, you're going to have to remember that there's always going to be one or two equations. There's going to be a primary and a secondary equation. And in this case, our primary equation is going to be the distance formula. And so if we're going to set up our distance formula, you have to remember that we're going to subtract the x's from each other. So x minus 0 squared plus y minus 2 squared. And then the issue becomes, well, I don't want this all in terms of x and y. I need it in terms of x. So I do know my secondary equation. I know that my y value is 4 minus x squared, so I can replace my y value in this equation down here with 4 minus x squared. So my new distance formula equation is really going to be, and I'm just going to simplify this down to x squared, plus, and then I've got 4 minus x squared minus 2 squared. And so that is my distance formula that I'm dealing with. And so I'm going to try to get things kind of combined together to make my life a little bit better. I've got x squared plus 2 minus x squared squared. And so then I have to multiply this part out. And when I multiply that part out to get things a little bit better, let's see, I've got x squared, and then I've got 4 minus 4x squared plus x to the 4th. And so combining some like terms and getting this thing into one nice neat little distance formula, I have x to the 4th minus 3x squared plus 4. Alright, so now I'm at this point and I need to find how I can get the minimum distance. And so the minimum distance, I'm going to use my derivative to find maximums and minimums. That's what I always do. And so what you have to understand at this point to make our lives easier, instead of doing a chain rule on this thing, I'm actually going to get rid of the square root, because I know that if I have the square root, I know the square root of 9 is smaller than the square root of 16. And if you think about that, the smaller the number underneath will still be the smaller number. So I don't need to use the square root. So what I'm going to differentiate, the function that I'm going to differentiate, is this function without the square root. So my f of x function is really going to be x to the 4th minus 3x squared plus 4. And so when I differentiate this thing to find my minimum, I'm going to get 4x cubed minus 6x. And with a little bit of work on this, I can simplify it a little bit to make my life easier. For example, pull out a 2x and get 2x squared minus 3. And so setting these guys equal to 0, which is really what I need to do, setting that equal to 0, I can go ahead and solve this, and I know that I have x equals 0, or x is going to equal plus or minus the square root of 3/2. And so at this point, I know, well, I don't know this for sure, but these are my critical numbers of this graph. And so I'm looking at the critical numbers of my distance, and I know that if I was to do the first derivative test, so I am going to do f prime of of something. And so if I go ahead and do my f prime of 0, if I plug these guys in, well, if I do my first derivative test and find out what's happening around these points, so let's see, here's 0, here is negative square root of 3/2, and here is square root of 3/2. Whoop, I lost my pen there. Square root of 3/2. And if I pick around points around these, let's see, if I do, let's go with square root of 3/2. Let's go like -2. I don't think that's good. So if I pick f prime of -2, plugging that into this, let's see, plugging that into this function here, into my f prime, let's see, I get a negative and a positive. So let's say 2, 4, 8, 32, positive or -32, and a positive 24. So that means I get a negative. So I am decreasing to that point. If I pick something like, let's say -1, if I go to the, like I said, the square root, if I put -1 into this function to find out what's happening in the middle here, you can see that if I put -1 in here into my derivative, I will get a -4, and over here I'll get a +6, which means I get a positive, so I'm increasing. So you can see there's a minimum at -3/2. If I put in something like f of +1, just going around these values here, f of +1, I get +4 and -6, so I'm now negative, so I'm now decreasing. And then after that, if I said something like f of 2, I would get +32 -24, or -12, which gives me a positive in this case, so I am now increasing. So my minimum values are when my x is square root of 3/2 and negative square root of 3/2. Those are my minimum, where I can get 0 as my maximum by my first derivative test. And so the closest points that I'm going to deal with are going to be my x value of negative square root of 3/2 and x value of positive square root of 3/2. And then if I plug these back into my original function, I could find out that my x value, my y values, my point comes out to be 5/2 for both of them. And since this is a parabola, they would have the same values for those values. So that's really what we're talking about when we're dealing with this function. So then the next one, if we're trying to find minimum area, and I made a little picture of it, so here's the picture that we're going to deal with. We want to find out what happens when we are trying to find, so this one, we're a rectangular page containing 24 square inches of print, and at the top and the bottom we have margins of 1.5 inches, and the left and the right we have margins of 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So basically some kind of cost-effective way of doing this. And so our primary equation in this case is going to be dealing with the area of the paper, because that's what we're trying to deal with. And so if I make, as you can see, they made x this vertical distance, so that would mean that I would have something like x plus 3 for that dimension, and I'd have y plus 2 for the other dimension. Then if we wanted to find the area of the printed part, then we would say, well, we know that the area is going to be x times y, but we also know that we're going to use 24 square inches for x times y. And so at this point, we need to substitute, we need to replace x or y with into one of our equations, and probably our best bet is to solve this thing for y. And so this equation would turn into y equals 24 over x. So now I can replace the y, just like we did in the previous equation. We're always going to do that. We're going to replace one of the variables because we don't want to do implicit differentiation unless we have to. So I'm going to replace that in there, and so my area equation, the one I'm going to find the least amount of paper, to minimize this, I'm going to use x plus 3 times replacing my y with 24 over x plus 2. And so now I can go ahead and differentiate this, and when I differentiate this, it's going to be dA with respect to x, the area, change in area with respect to x, which basically is going to cause me to do a product rule on this. And so when I differentiate the first, I get 1, and that's times 24 over x plus 2. And then add on, leaving the first, and I'm going to get rid of this. And differentiate the first, or leave the first. It's supposed to be a 3. Differentiate leave the first alone, and then multiply it by the differentiation of the second, which is basically negative 24 over x squared. And so now with a little bit of simplification on this, I can kind of get this thing into a little bit better form. 24 over x plus 2 plus, and then this guy becomes, well, we got to distribute, negative 24 over x minus 72 over x squared. And then, well, you can see these guys, my 24x's will cancel out, and so I'm left with 2. So my dA dx, these guys cancel out, and so I'm left with 2 minus 72 over x squared. And so that's my area function. And so then if I set this thing equal to 0, you could go ahead and find out what's happening. I would add this thing across the equal sign, so 2 will equal 72 over x squared, multiplied by x squared, so 2x squared equals 72, divide by 2. And so x is either plus or minus 6. And so if that's the case, then obviously we're not going to consider negative 6 as part of the solution because, one, we can't have a dimension of negative 6. So our dimension would be x is 6 in this case. And then, so then that's not the dimension that we're looking for because we need the dimensions of the page. So we got to go back and say, oh, well, if x is 6, then we know that y would have to be 24 over 6, which would be 4, but that goes, we got to go back to our dimensions. So the dimensions we need are going to be 9 by 6. That's going to be, this was the 6 plus 3 by 4 plus 2, plugging back into my original area function. And so 9 by 6 is really what we're looking for to minimize the paper that we're going to use and also maximize the type. So then we're going to find a minimum length, and just so you know, not all of these guys are minimums, but we're going to go through and say, okay, we need to find the minimum length of we have 2 posts 12 feet high and the other one 28 feet high, and so I'm going to pull out a picture here so you can look at it. They stand 30 feet apart. They are stayed by 2 wires, so those are the 2 wires, the Y and the Z wire, and attached to a single stake. And we need to find where should that stake be placed for the least amount of distance. So our primary equation in this case is going to be our wire is going to be y plus z. That's our primary equation. The problem is we don't like that. We don't like using all those different variables. So we're going to have to go through and solve for both y and z with a third variable, which is kind of a troubling for us, but that's all right. You'll notice they gave us dimensions. They gave us x was this distance, 12 was this distance, so we could use Pythagorean theorem to find out what y is in terms of x. So we know that x squared plus 12 squared will equal y squared. So we know that y is really the square root of 12 or of 144 plus or x squared plus 144, which we can write out. So we've got x squared plus 144. All right, and then our z value is going to be a little trickier, but it's going to be 28 squared. 28 squared plus 30 minus x squared. So now that we have all of these in terms, and we can multiply this out, and so basically with a little bit of work and stuff, and I'll let you multiply it out and everything, z comes out to be the square root of x squared minus 60x plus 1684. All right, so now that I've multiplied that all out, I'm going to replace x, y, and z with what I've got for them. And here's my y, here's my z, and this thing's going to look a lot uglier than it did from the beginning, but the good news is it's all in terms of x. So I've got x squared plus 144 plus my z value, which I don't know if I've got room for, x squared minus 60x plus 1684. All right, so there we go. There's our new function. And so we know that we have to be between 0 and 30 because the posts are our domain is going to have to be that x is going to be less than or equal to 0. Wait, 0 is going to be less than or equal to x, which is less than or equal to 30. Sorry. 0 is less than or equal to x, which is less than or equal to 30. So we know that we have to fall within that range. And so now we have to differentiate this function. And unfortunately, well, good news is it's just two chain rules, but it's not any product rules or quotient rules or anything like that. So w with respect to x becomes, well, this is a chain rule, so differentiate the outside, which gives me a half. And then when I differentiate the inside, I get times 2x. And then on the bottom, the thing goes to the bottom, so that leaves me with x squared plus 144. Same idea is going to happen with this guy, except for it's going to be 2x minus 60 all over 2 times the square root of x squared minus 60x plus 1684. All right, so that's my differentiation, and I can do a little simplification to make my life a little bit better. Probably should do that, get rid of the 2's and things like that to simplify this a bit. So let's do that real quick. When I simplify that, I'll end up with x over the square root of x squared plus 144, and over here I have x minus 30. X minus 30 over the square root, that big long square root, x squared minus 60x plus 1684. All right, so now if I was to set this thing equal to 0, I can move one of these guys across the equal sign and cross multiply them to make my life a little bit better. And so that's what I'm going to do. I'm going to move this guy across the equal sign, which will give me x over the square root of x squared plus 144. Now, my maneuver to change the signs is I'm actually going to change the sign on the top because that will make it negative. And to do that, we'll just actually reorder those guys. And so I'm looking at something like this. And that's just kind of an algebraic maneuver to make things a little bit easier for myself when I'm going through so I don't lose my negative signs. And if you didn't do that, if you just put a negative parentheses and negative or whatever, made the whole thing negative, it'd be fine. So now I get to cross multiply these things, and so x equals times the square root of x squared minus 60x plus 1684 equals 30 minus x, all of that times the other square root of x squared plus 144. So I get something that looks like this, and then unfortunately I have to multiply. I'm going to square both sides. That will remove the square roots, and yeah, that'll help a little bit. This side becomes x squared times this thing, and over here I get my 30x. 30 minus x squared, and then I lose the square root of that. And so when I multiply all this side out, I get x to the fourth minus 60x squared, x cubed plus 1684 x squared. And then on this side, I'm going to multiply it all out, and it becomes very nasty, but I've already done the multiplication, so I'm going to just write it out. And so now I've got this, and if I move things across the equal sign, you'll notice I lose my x to the fourth, I lose my x cubes, I will lose some of my x squareds. So these guys go away, which is good for us. We lose some of my x squareds. My new x squareds is approximately 640 x squared. If I move this guy across, there's no other x's, so I have 8640x, and then I'm minusing this guy from both sides, and so now I have a quadratic that is equal to 0. And surprisingly enough, that if you don't see it, you could use the quadratic formula. I do have 320 in common, and I can factor that out. That helps a little bit. It will leave me with something. Well, that'll leave me something that's factorable, and I can factor it to this. And then finally, I end up with x either is 9 or x is negative 22.5. Well, the negative 22.5, again, is outside the domain, so we're looking at x equals 9. So on one side, the wire will be, if we're trying to find our maximum distance or our minimum distance, we're going to check all of our points. And so we would say, well, what if we just put it right at 0? If we put it right at 0, then we would end up with approximately 53 for the length of the wire. If I put it at 9, we would end up at exactly 50. And if I put it at 30, which is my other option, my other endpoint, I'm going to end up with 60.31 feet of wire. And so all of this basically is that we need 9 to use our minimum amount of wire between them, which would be the 50 feet of wire. All right, so then our final example is finding the maximum, and I'm going to pull a picture out here just so you can see them. We have 4 feet of wire to be used to form a square and a circle, and so how much wire should be used to be used for the square, and how much should be used for the circle to enclose the maximum area. And so first thing I'm going to do is write a primary equation, and the primary equation that we're going to use is the area of the circle, which is pi r squared, plus the area of the square, which would be x squared. And you can see that from the dimensions over there, which doesn't help us a whole lot. We know that the perimeter of these, which is what we're trying to fence in, the perimeter is going to be 4, because we need it to be 4 feet. And the perimeter of a square is 4x, and the perimeter of a circle is 2 pi r. And so if I was to solve this for r, to try to make my life a little bit easier to get it in terms of x, let's see. Well, I'd have 4 minus 4x equals 2 pi r, and then if I divided by 2 pi across the equal sign, I would end up with r being looks like something like 2 minus 2x over pi. And so that's what I'm going to replace my r with in my area equation, in my primary equation. And so if I replace my r with that, my area, all in terms of x, is really going to be, well, the pi's will cancel out, which makes it kind of nice. Well, actually, no, hold on. I got to do this first. I got to say pi times 2 minus 2x over pi squared plus x squared. And so, yes, I have to kind of multiply this thing out, and when I'm not gonna go through it right now, but you'll notice I have a pi squared on the bottom, so really my area as a constant multiple will be 1 over pi times 2 minus 2x squared plus x squared. And the reason I don't want to multiply this out is because I can just do a chain rule when I differentiate it, and we'll be good there. And so if we basically we're going to go ahead and differentiate this. So if I go ahead and differentiate this in terms of x, I'll leave my 1 over pi alone, and then follow my chain rule 2 times, let's see, this left alone to the first power. I was going to write a 1 there, and then this guy becomes negative 2, and then we're going to add on a 2x. So there is my differentiation. And with a little simplification, it comes out to be something like, let's see, 2, 4, 8, negative 8 plus 8x over pi plus 2x. There's my simplification. I could get this, if I multiplied by pi, then I would have this all is 1 fraction, which might help us. Since that's really what we're trying to find, we need to set this thing equal to 0. And so by setting this thing equal to 0, the pi will go away. Subtracting 2, well, I can't do that. I can go ahead and solve this, and basically x comes out to be, when it's all said and done, x will come out to be 4 over pi plus 4, which is kind of an ugly number, and so that's approximately 0.56. And so we know that that's going to be, if we're trying to maximize this, we're trying to find the biggest area. And so if we're going to find, we're going to use our region, and our region is that we could have our x value be between 0 and 1 to get our dimensions, to get a perimeter of 4 and an area of what we're looking for. So if that's our case, then we could say, oh, well, area at 0 is going to be approximately 1.273. Our area at 0.56, just putting in our x values, is approximately 0.56, and our area at 1, which would be our other endpoint, is approximately 1. So if we want to find the maximum area that occurs, it's when x is 0. So all the wire is going to be used for the circle. This is our maximum area, so all wire will be used for a circle. And so this concludes section 3.7, optimization. If you have any questions, please come to class. Please look up other videos, and I'll be seeing you guys in class.